Welcome back, everyone. Sorry about the little delay. We are beginning day 4 of the hands-on workshop, Programming and Optimization with Intel Architecture. Allow me to quickly review to overview the course. This is a 10-day workshop followed by 5 days of self-study with remote access. We are in day 4. Today is September 14th. And the topic today is expressing parallelism with multithreading. This will be a crash course on OpenMP. This course has a web page, colfaxresearch.com how 1509, and you can also go to this page from a link that you have in the reminder email that you received just about an hour ago. This page contains slides of the webinar that I'm running now, and also recordings of earlier events. Here is the page, and it has the schedule, and here are the recordings of earlier sessions, and the slides and the code that we're dealing with today. You can download them from this page. The original source of all materials for this course is our original book, Parallel Programming and Optimization with Intel Xeon Phi Coprocessors, the second edition. All the topics that we discuss in the course are also in the book, and the book actually has a bit more information. Also, this is the source for all the practical exercises that we are running. This is a hands-on workshop in the sense that we give people remote access to a training server, and you can log in and experiment with the exercises that I'm demonstrating in the second hour. If you don't have remote access, either the waitlist will soon trickle down to you, or you can just follow along with me in the second hour of every broadcast. If you attend 6 sessions or more out of 10, we can issue to you a certificate saying that you have successfully completed this course in the fundamental level of accomplishment. And visit us at colfaxresearch.com for even more information on parallel programming. We had a weekend between this session and the previous one, so I think it's a worthwhile use of a couple of minutes to quickly review what we talked about earlier. This is a course on programming the Intel parallel architecture. We are focusing on only 2 architectures, Intel Xeon processors and Intel Xeon Phi coprocessors. What we are discussing in terms of parallelism, memory access, and optimization applies to both of them. The difference is that Xeon is more versatile. It can compensate for inefficiencies in your code. But Xeon Phi is more specialized. So on the one hand, it requires that your code be more fine-tuned in the way that it uses parallelism and memory access. On the other hand, if you have a well-tuned application, it will run better on a Xeon Phi coprocessor than on a Xeon. At the same time, everything that we discuss in terms of optimization applies both to Xeon and to Xeon Phi. The first 2 episodes of this course focused on using Intel Xeon Phi coprocessors, and we mainly talked about how to run something on a Xeon Phi coprocessor, not necessarily in parallel or not even efficiently. And in this context, we talked about 2 programming models for Xeon Phi, offload programming and native programming. Offload programming is when you start the application on the host, and then parts of the application are pushed to the coprocessor and executed there. This is an instance of offload, and we talked about 3 APIs for offload. This is a demonstration of one of them called explicit offload with language extensions for offload, LEO. Another approach to programming Xeon Phi coprocessors is native. This is when you run the entire application on the coprocessor and the host is not used except for possibly except for booting the coprocessor and possibly handling some of the network traffic or file I/O. Then in session number 3, we started talking about parallelism. And at this point, the discussion becomes common to Xeon and Xeon Phi platforms. We talked about vectorization, which in the context of Intel architecture is synonymous with SIMD. SIMD stands for single instruction multiple data. So every core on a Xeon processor or a Xeon Phi coprocessor has machinery for processing multiple data elements with one operation in one instruction. This machinery, specifically for the Xeon Phi architecture, is referred to as VPU, Vector Processing Unit, and the vectors on which a Xeon Phi can work are 512 bits long. If you translate this to single precision, 512 bits is the amount of data in 16 single precision floating point numbers. So if you're adding arrays A and B, you can take 16 values of A, add them to 16 values of B, and store them back in memory. And each of these will be a single vector instruction. As for Xeon, the width of the vector registers varies with generation, and in the latest Haswell architecture, the vectors are 256-bit wide. Things you can do with vectors include, well, memory accesses, including sequential memory accesses, load and store, and strided memory accesses, gather and scatter. Of course, with vectors, you can do traditional arithmetic operations, plus, minus, divide, multiply. You can also do transcendental function calculation. There's support for reciprocal square roots, exponentials, and logarithms. And many other transcendental functions have analytical approximation that build on these on this hardware support. You can also do comparison with vectors and type conversion between, for example, integers and floating point numbers and back. Or you can use the entire vector to run 512 bitwise instructions in one instruction. Xeon Phi also supports reduction and minimum maximum instructions, which are not really vector, they're more sequential, but they are available. And mask instructions are also supported so that you can use branches inside of vector loops. We talked about how to use automatic vectorization. The primary access to it, which is portable and future-proof, is automatic vectorization. This is when you write a loop and you expect the compiler to implement vectorization for you and handle all the runtime situations regarding alignment and loop length also for you. We also learned how to diagnose automatic vectorization using the argument qopt report and viewing the optimization report file. And also we talked about two more ways to express automatic vectorization: array notation and SIMD-enabled functions. I'm not going to review them in detail now, but if you're interested in that, you can go back to session number 3 and watch the video or download the slides. Today we are going to talk about another level of parallelism available in Intel architecture. On the hardware level, this corresponds to multiple cores in Xeon processors or Xeon Phi coprocessors. On the software side, handling this parallelism is done with multi-threading, and we will talk about expressing multi-threading with OpenMP. In Intel platforms, you can view both Xeon and Xeon Phi as symmetric multiprocessors. So they have multiple cores. On Xeon, this is up to 18 cores per socket. On Xeon Phi, this is up to 61 cores on a chip. Each core represents itself as 2 logical processors on a Xeon or 4 logical processors on a Xeon Phi. This is the hyperthreading technology on Xeon, or 4 hardware threads on Xeon Phi. And usually each of these logical processors will accommodate a software thread. meaning a program running independently in each logical processor. Of course, the reason why this is an attractive architecture is that there are um, some shared elements to it. For example, all cores or all logical processors have access to memory, which is shared between them, and this memory is cached, and caches are kept coherent across different cores. So whenever thread running on this logical processor modifies something in memory, these modifications will be available to threads running on other logical processors. And we will talk today about how to make it so that this works in your favor as opposed to producing incorrect results. Also, something to keep in mind is when you have multiple threads running on one physical core, they all share the vector unit. So they will take turns, depending on the architecture, on demand or predictably. They will take turns using the vector unit and running vector instructions in the core's vector unit. There is one vector unit on the first generation of Xeon Phi coprocessors. The second generation will have 2 vector units and 4 logical processors per core. Having cores and vectors in the platform requires you to think where you have parallelism in your application and specifically focus on task parallelism and data parallelism. Cores can handle task parallelism, meaning they can run independent streams of instructions and they can access memory in any way they want. To utilize cores, you have to use software threads, and we will talk about a framework for doing that called OpenMP. With vector units, which are present in every core, vector units are present in every core, so vector units essentially implement a second level in the hierarchy of parallelism. And vector units are devices for data parallelism, meaning that they have to run the same stream of instructions on different data elements. Vector units must operate on contiguous vector registers, so before you can run math on multiple numbers at a time, you have to load them from memory, and that will be a complication. And that could be a complication in some algorithms. And to use vectors, you have to have vector instructions in your code, and rather than inserting them with assembly or with intrinsics, as we discussed in the previous episode, it's best to use automatic vectorization. I also have a line in this table that indicates the number of cores and the number of vector lanes. I just want to point out that the number of cores is anything but a power of 2 usually. Well, in Xeon Phi you can have 61 active cores. As for vector lanes, the number of vector lanes is usually a power of 2, corresponding to a power of 2 bits in the vector register. So we will talk about multi-threading, and we will focus on, among other things, on writing applications in such a way that they are not dependent on how many exactly cores you have. You should be able to design an application that runs on 2 cores just as well as on 18 cores, just as well as on 61 cores. And this is my favorite graphics here illustrating the types of workload that are suitable for vectors and for cores. So vectors are for data parallelism, meaning different data elements, the same program, like these 2 zebras are doing grazing on 2 different patches of this field. And cores are for task parallelism. Potentially, cores can implement data parallelism, but they don't have to. Each core can run an independent program. One core may be thinking about the meaning of life, and the other core may be thinking about something to eat. This is the difference between the purpose of them. You may find that some applications naturally have 2 levels of parallelism that can be handled by these 2 hardware systems. These applications are such that you can parallelize the outer loop and vectorize the inner loop. And this is an example of code that will actually do that. This pragma we have not studied yet, and we will talk about this today. And some code, some applications are actually all data parallel. In this case, you can distribute workload both between across vector lanes and across multiple threads. So after this lengthy introduction, I think you are all ready to start talking about multiple threads. And we will talk about a framework called OpenMP. This is a framework for multi-threading. I think it's best to begin introduction into OpenMP with an example. And here is an example. This is the Hello World application in OpenMP. This application is the main function, which starts executing in one thread. And here I query how many threads I have available. Later in the application, I have a directive, pragma OMP parallel. And in the scope of this pragma is some code, and this is the code that will be parallelized. So let me demonstrate how it works, and then I will go one step back and explain what OpenMP is and what it is for. So the next step, we are going to run this code, and we will see this line printed once and that line printed many times. When I compile the code with the Intel compiler, I use the argument QOpenMP to link the OpenMP runtime library. And then I can control the number of threads using this environment variable OMP num threads. When I run the application, the line outside of the scope of the parallel pragma is run once, and all the code inside of the scope of the pragma is executed many times, and different threads have different IDs. So this is what OpenMP is. This is a library and also a standard for running multiple running multiple threads. OpenMP stands for Open Multiprocessing, and it operates by including directives in your application. OpenMP is supported for C, C++, and Fortran. Well, actually it has C and Fortran bindings, but it compiles as C++. So everything that I talk about will show syntax in C, but mind that the same syntax is applicable to Fortran, except that instead of a pragma, you will have a different keyword. And the multiple threads, the purpose of them is to utilize multiple cores available in your platform. OpenMP can scale across all the cores that you have in the shared memory system, but it cannot scale across multiple systems. So you cannot use OpenMP to run an application in a distributed memory system such as a cluster, nor you can use OpenMP to create threads simultaneously on the host and on the Xeon Phi coprocessor. For this, you will have to combine the offload programming model with OpenMP or the native programming model with MPI and OpenMP. So threads, you can think of them as streams of instructions sharing the same memory address space. This is distinct from processes. If you run multiple processes, you cannot have variables that are available to all of them. But threads do exactly that. You can have a variable that is available to all of your threads. By default, all variables declared at the beginning of the function or at the beginning of main will be available to all threads in the OpenMP region. The proper term for this is they're going to be shared across all threads. This sharing of variable is sometimes what you want. Other times it is counterproductive. When would you want to share variable between threads? Well, one obvious case is when this is read-only data. For example, you have a physics simulation which has geometry, and then it has multiple particles that you're going to propagate. So the geometry you might want to share between all threads, because if you replicated geometry across all threads, you would be using more memory than you have to. As for particle data, you might distribute particle data data for different particles between different threads. And in this case, you don't want to share this data. Possibly you might want different threads to work with different particles. Other situations where you don't want variable sharing is in parallel patterns, such as reduction. We will talk about these parallel patterns later, and this is related to performance optimization. So, to control which variables are shared and which variables are not shared, OpenMP has two clauses, private and shared. Well, shared in fact replicates what is happening by default, except that you can use it to you can disable the default behavior and use shared just to control that you didn't forget any variables. Private, this is the new clause. Private makes variables listed in the parentheses private to each thread. This means that when the parallel region begins, OpenMP will create a copy of this variable A for every thread. This copy will not be initialized. To initialize this copy, you can either initialize it inside of the parallel region or use, instead of private, use the clause first private, which will also initialize it. This is an approach that works in C and Fortran, and this is well supported in all OpenMP implementations. If you are using C but not Fortran, you have another way to control variable sharing, and that is using scoping. In C, you can declare variables right in the middle of your function if these are stack variables. And here I declare B at the beginning of the function before pragma OMP parallel. And there I declare variable I inside of the scope of pragma OMP parallel. So when I enter the scope of pragma OMP parallel, OpenMP will create multiple threads, and each thread will run whatever program is inside of these parentheses. And for each thread, I request the allocation of this variable. So automatically, when I use this variable in this code, it will be private to this thread. And when I modify the value of this variable in thread number 0, all other threads don't see this modification. So this is one feature of OpenMP that makes writing applications easy. Control of I shouldn't probably say this. This is one of the features of OpenMP that has support for commonly used features in parallel HPC programming. Another feature that OpenMP has that's common in HPC is support for parallel loops. If you have a loop with multiple iterations and different iterations can be executed independently, you can distribute these loop iterations across different threads. OpenMP has support for distributing these loop iterations across different threads in such a way that you are not bound to the number of threads in your application. I'm sorry, in your system. This is how it works. I have a loop. The loop counter I runs from 0 to n. And to make this loop run in multiple threads, I will put pragma OMP parallel, followed by the keyword for. The keyword for says that OpenMP, I want to create multiple threads, but immediately I want to team them up to process this parallel loop. Different iterations will be distributed across different threads, and exactly in which pattern they are going to be distributed depends on the scheduling mode that you can specify in this clause. We will talk about scheduling modes later. When I write pragma OMP parallel 4, I'm actually combining two pragmas, pragma OMP parallel and pragma OMP 4. So there is an alternative way to write parallel loops. You can start a parallel region. This will create threads. Each thread will run whatever code I have between lines 3 and 8. And then line 9 says that I want to team up all threads to execute this loop in parallel. Notice that in this line, I do not have the keyword for. I just have pragma OMP 4. Scheduling modes that you have available are static, dynamic, and guided. We will focus on them some more when we talk about performance optimization, but here is a quick overview. Static decides at the beginning of the loop which thread will run what iteration, and this is not changed at runtime. Dynamic is the opposite. It distributes some iterations between available threads, but then it holds off until one of the threads finishes with its workload. At this point, the scheduler will give this fast thread the next iteration. And so on. Dynamic will keep distributing iterations across threads until the application is done. Obviously, you can see the difference. Static has a very low overhead on scheduling, but if you have load imbalance, static will not compensate for it. Dynamic is different. Dynamic has high overhead for load balancing, for scheduling, but it can do load balancing.
Richard, dial 4120.
Sorry about that. That will not happen again. Dynamic is different. It has high scheduling overhead, but it will try to load balance as much as possible. Guided is the third scheduling mode. It is a trade-off between static and dynamic. It begins by distributing large chunks of iterations, and then as the application progresses, guided hands out smaller and smaller chunks so that it has low enough scheduling overhead and opportunities for load balancing. Besides the type of scheduling, you can specify the chunk size as the second parameter in the scheduling clause. And the chunk size is how many iterations are assigned in every scheduling cycle. So for the static scheduling mode, chunk size means that a chunk size of 1 means that I will assign one iteration to each thread, and then I will go in round robin. For dynamic scheduling, chunk size of 2 means that I will hand out 2 iterations at a time to each thread. In guided mode, a chunk size of 2 means that I will start with large chunks, and then I will decrease the chunk size more and more as the application progresses, but I will never hand out fewer than 2 iterations. And OpenMP is smart enough to handle situations when the number of iterations that you have is not proportional to the number of threads times the chunk size. It will try to, it will execute the loop correctly, it will execute all iterations, and it will try to load balance as much as possible. For parallel loops expressed with the for loop are a very powerful feature because this is what a lot of HPC applications are built around. But in some cases, you may want to use a different pattern of parallelism. And as a parallel pattern, this is called the fork join model. Sometimes you may want to have a task that creates a child task, and these two tasks can potentially run in parallel. And eventually you can recursively create a tree of tasks, and then you have the job of scheduling these tasks across available threads. OpenMP has functionality for this type of parallel pattern as well. And the clause in OpenMP that does that is task. So this is OpenMP task functionality. This is useful, for example, to implement parallel recursion. And we will see, for example, in session 9, that parallel recursion is a powerful method for some optimization techniques. For example, memory traffic optimization can be done by using recursive cache oblivious algorithms. This is an example of using OpenMP tasks to implement recursive divide and conquer. I have two panels here. The panel on the left initiates the recursion. The panel on the right is the recursive function. So for now, let's pretend that these pragmas are not in the code. Pretend that they're not there, and then we have a serial code. In the serial code, I just call the function recursive fork load. So what's happening in this function? Inside of this function, first I do a check. Is the size of the problem small enough? If the problem is too large, then I will split it. And this is how I split it. I create a set of arguments which corresponds to the first half of the data set hiding behind this argument set. And then I create the second half of the data set. After that, I call this function twice, recursively, first on the first half of the data set and then on the second half of the data set. And this is what I do if the problem size is too large. If the problem size is not too large, then I end the recursion and I process the smallest subtask that I have in my problem. So I think the serial code is more or less straightforward. Such code you may find, for example, in the implementation of a common numerical method, the Cooley-Taki algorithm for fast Fourier transforms. Or a similar algorithm occurs in the quicksort sorting algorithm. How do we parallelize it? If the logic of the application allows me to run independent, to run different parts of the problem independently, then I can potentially put them into OpenMP tasks. And the syntax for expressing this tree of tasks will look like this. I will start a parallel region, and immediately I will restrict execution to just one thread. Then I will start one instance of my recursive function. So one thread will be working, all other threads will be sitting there waiting for tasks. When I enter this function, I will start splitting up the problem, and I will start putting different subsets of the problem into different tasks. As soon as I have tasks to work on, other threads will begin processing them, and it is okay to have many more tasks than I have threads. What I've discussed so far is how to parallelize your algorithm as much as possible, how to put different iterations of a loop or different tasks into different threads. And this is usually not the hard part. The hard part is typically making sure that all of these threads don't run wild, that they actually produce correct result. And this is what we will talk about, thread synchronization. Consider this example. I have an application that has a loop. The loop counts from 0 to 1000, and what it does inside of this loop is it sums all integers from 0 to 999. This is not a particularly meaningful application because I know the analytical result. I know what the result should be. So I don't have to do it computationally, but this is just an illustration for what can happen in similar applications. When I've computed this loop, I will print the result as I computed it, and then I will print the analytical expression so I can compare the results. And let me try to parallelize this loop. I will use OpenMP. To do that, I will put pragma OMP parallel 4 before the loop, and it says that OpenMP, I want to create threads, and I want to distribute these loop iterations across different threads. And OpenMP will detect how many threads I have available I can run in this platform. It will schedule these loop iterations across different threads. The variable total will be shared across all the threads. And supposedly when I increment this variable total, I should get the correct result. Turns out that when I run this application, the result is different from the analytical prediction. It's actually smaller. And even more, if I run this application many times, the result will be different every time. That is because I have here what's called a race condition or a data race. This occurs when multiple threads access the same element in shared memory, and one of these accesses is writing. So it's okay to access the same memory address for reading, but if you're accessing by multiple threads. But if you're accessing by multiple threads the same memory address for writing, problems can occur. And that's why this write operation is actually not one operation. I have to read the value of total. I have to add the increment to it, and then I have to write back in memory. So sometimes you can have one thread reading, incrementing, writing back. This is good. But other times you can have one thread reading the variable, and before it has a chance to do the rest, the other thread comes in and reads the old value of this variable. Then what might happen is at runtime, first one thread will write its own result, which is 3, and then the other thread will write its own result, which is 4, and the correct result should have been 6. But because of this data race, I got an incorrect result. So data races must be protected in parallel regions. And this is where the art of parallel programming begins, because you have to decide how to do it in such a way that your program is efficient and at the same time correct. Fortunately, you don't always have to treat it as art, because there are common parallel patterns, and I will discuss one of these parallel patterns called reduction. Um, to understand why parallel patterns are necessary and to learn the tools that we have for them, let me first discuss a feature, a functionality called mutexes. A mutex in parallel programming is a programming tool which implements mutual exclusion. This is what mutex stands for. Mutual exclusion means that only one thread can operate on a memory address or on a piece of code at a time. So when I have this operation with a race condition, I may want to say, well, I only want one thread to read this variable at any time. So I want this. One thread is reading, writing, it's done. Then another thread grabs this variable. Thread 1 must have to wait until thread number 2 increments, writes the results, and so on. So essentially, I'm serializing my application in this code region. One of the mutexes that you can use in OpenMP is pragma OMP critical. This is a directive that has a scope. Everything inside of the scope of this pragma is protected from parallel execution. So when one thread reaches pragma OMP critical, it may enter this critical region. Any other thread that comes to the entrance to this region must have to wait until that first thread exits. So only one thread at a time is able to enter this critical region. What it does is it makes my program produce correct results. As you can see, I recompiled, executed again, and the numerical result is identical to what I predict analytically. But the performance of this application is going to be even worse than the performance of a serial application, and we will actually see it in action. This is a terrible way to do that, in other words. Critical section is a very heavyweight mutex. It serializes the application. Sometimes this mutex is justified, but not this time, because what I am protecting this time is my entire parallel iteration. If I was protecting only a part of my parallel region, that would be acceptable, but I'm serializing my entire application. There is a more lightweight mutex, which may make things slightly faster, but still unsatisfactory. But let's see how it works. The mutex is now the atomic operation construct. Pragma OMP atomic is what you use to implement this mutex. This pragma does not have a scope. It applies to just one line. And this one line will be protected from parallel execution. Specifically, atomic constructs are only good for certain sets of operations and for certain data types. They work by relying on hardware functionality for atomic updates. The operations to which you can apply atomic mutexes are reads, writes, updates, and capture. And this you can only do on a single scalar variable. Operations that you can do for updates include summation, like we did in our example, or other types of arithmetics. You can also do, bitwise logical operations on these scalar variables. You cannot overload one of these operators and expect that a complex program will be correctly protected by an atomic mutex. This is really for just for atomic updates on scalar variables. So the atomic mutex is less flexible, but is also more lightweight than a critical section. Still, that implementation of the summation of numbers from 0 to n with atomic mutexes has poor performance. This is a case where you have to recognize that, okay, I can write my program so that it is a parallel program. I can write my program so that it is parallel and correct by using mutexes. But I also have to do something to make sure that my program is not just parallel and correct, but it is also efficient. And this is where this parallel pattern becomes very useful. This is possibly the most commonly used parallel pattern in high-performance computing, and I will illustrate it. The pattern is parallel reduction, and we will avoid excessive synchronization by using thread private variables. What I'm doing in this loop is I'm incrementing the variable total. I'm doing it by multiple threads concurrently. But the only operation that I'm doing with this variable total is this increment. Because this is the case, I can use built-in functionality in OpenMP for reduction, and all I have to do is to include the clause reduction and put plus. This is the type of operation for which I'm doing reduction. And then after a colon, I can specify the list of variables on which I do this reduction. In this case, it's just the variable total. So this will make my program parallel, correct, and efficient. As you can see, the result is correct. We can also do some benchmarking to see that it is efficient. The question is, what happened here behind the scenes so that this is efficient? It is very important to know the answer to this question, because this clause will not work always. It only will work when you are doing reduction into a scalar variable using one of the supported operators. Sometimes you may want to do reduction not into a scalar, but into an array. And in this case, the reduction clause will not work, and you will have to implement all of the machinery that happens behind the scenes by hand. So to illustrate what's happening, I will show a different implementation of this program that uses thread private containers. So here's what I'm doing here. I'm starting a parallel loop. Every thread will run this code. So every thread will create a variable total th. So this is a thread private copy of the variable total. And you can recognize from earlier slides that instead of doing that, I could do pragma OMP parallel private total, but I preferred to do this. Then I start my parallel loop, and I just type pragma OMP4, no keyword parallel. Then what it does is it distributes different iterations of this loop across different threads. And when I do my increments, I don't use the shared variable total. Instead, I use the thread private container total th. So each thread will accumulate a partial sum in this total th variable. And when the loop finishes, each thread will have a part of the sum. Now I have to add all these partial sums together to produce the shared result total. And I can do it by including just one line, total plus equals total th. This line is still inside of the parallel scope. So this line is executed as many times as I have threads, and I will be accumulating values from every thread into this variable total. Also, you can recognize that this is a data race, because different threads will be accessing the variable total at the same time, and there is no guarantee for the order of operations. So I protect this race condition with the lightweight mutex pragma OMP atomic, and when I get the result, it will be correct, and the program will be quite efficient. This may not be the best way to implement reduction, because I am doing as many atomic operations as I have threads. Potentially, I could get away with log n of threads operations. I'm sorry. If n is the number of threads, I could potentially do reduction with log n uh, atomic constructs using a tree reduction algorithm. But as long as the bulk of the computation takes much more time than the reduction operation, this really doesn't matter. So this is what OpenMP does behind the scenes when you use the reduction clause. The reason I showed this is, well, for one thing, this is a perfectly correct way to implement this parallel program. And second, this is the pattern that we will use a lot in this course, and it will be our only option when the reduction variable is not a scalar but an array. So summarizing, we are discussing the second level of parallelism, multi-threading, which is designed to utilize multiple cores in the system. When you use threads, I'm sorry, when you, yes, I apologize for the distraction. We're discussing multi-threading, which is the way to use multiple cores in your platform. Every core in Intel platforms has vector processing facilities. So sometimes using vectorization inside of every thread is the best way to go about parallelizing your application. This means that typically you will target your implementation of the parallel algorithm in such a way that you have two loops where you can parallelize the outer loop across threads, and where you can expect the inner loop to be parallelized across vector lanes. If you have multiple loops, typically you will try to parallelize across threads as far out as possible, and you will try to parallelize across vector lanes as far in as possible. Other times, applications are so highly parallel that everything is data parallel, and you can actually combine multi-threading with vectorization in one loop. For example, doing that, the compiler may be able to implement OpenMP parallelism with together with vectorization in this loop. Of course, it depends on the complexity of the code here. There are cases where your entire application is essentially one loop, but the compiler is not able to handle multi-threading together with vectorization. This is where you will use some additional programming techniques to help the compiler to expose opportunities for vectorization. One of such programming techniques we will discuss later is strip mining. This is where you take a loop and represent it as two nested loops, where the innermost loop has unistride access and you can parallelize it, and the outermost loop and the loop in the middle you can actually combine with the outermost loop in the parallel iteration space. So here you can see I'm using the clause collapse. It tells the OpenMP runtime that I want to parallelize not only this loop, but actually the Cartesian. I want to parallelize across the Cartesian product of this iteration space of this loop and that iteration space of the second loop. Parallelizing an application is typically more complex than just inserting pragma OMP parallel 4 here and there. And the best high-level strategy that you can adopt is, in the words of James Reinders, take a deep breath and think about where parallelism is in your application. We have an interview with Intel's James Reinders, who is a technology evangelist specializing in parallel programming at Intel. You can view this interview by clicking this link, or if you're interested in the quote that I've just given you, you can click the thumbnail in the slides. And James has a brief discussion of the logic that you can use to decide where parallelism is and how you would use it to write a parallel code that runs well on Intel platforms. For a specific example on what we discussed, you can refer to this tutorial. This is a 12-page paper which uses the same physics-motivated example to illustrate parallel reduction. I have particles coming in into a cylindrical detector, and these particles have polar coordinates, and my job is to count the number of particles in different bins on a Cartesian grid, so that, for example, I can detect tracks or run any type of analysis. This paper demonstrates how to do this efficiently with multi-threading, and there is a second part of this paper which I referred to in the previous broadcast. It discusses vectorization. For more, yes, the presentation on OpenMP that I have just given was a 30-minute crash course. I hope this is enough for you to be able to understand the examples that we have in the hands-on part. But I do not expect that I really did justice to this framework. And I want to refer you to some additional materials that you can use to learn more. Intel OpenMP specifications are available online. This is a long, dry document explaining the API of OpenMP and explaining also what the implementation is expected to do in different scenarios. So this is a manual. For something more educational, you can view this 2-hour video course. If you prefer to learn from written materials, you can either go to this very convenient tutorial from the Lawrence Livermore National Lab, or you can refer to our book. We also discuss OpenMP in greater detail than I was able to do in this 30 minutes. So today we discussed that there's 2 levels of parallelism in Intel platforms. Vectors, this is what we learned to leverage in the previous lesson, and cores. To use cores, you must use threads to scale across them. Threads all share the same memory address space, so you may have race conditions, that is when different threads access the same memory location for writing. Race conditions lead to incorrect and unpredictable results. You can use mutexes such as OpenMP critical sections and atomic operations to control race conditions, but this costs you in performance. So sometimes you have to use parallel patterns that are economical in how they use synchronization. Multithreading must coexist with vectorization. Sometimes this is natural when you have nested parallelism in your application. Other times you may have to help the compiler to have them coexist. We discussed OpenMP. This is a very well-established parallel framework, often used in high-performance computing applications. And this is not the only framework for running multiple threads. You can use pthreads, Silk Plus threading building blocks, boost threads. We are talking just about OpenMP because it has a lot of functionality for high-performance computing built in, and we find this convenient. I have not really talked about optimization of multi-threaded applications. I am not able to do this in 1 hour because this is really a long topic. And we have 2 sessions coming up on optimization of multi-threaded applications. These will be sessions number 7 and 8. And in our calendar, I believe they are Thursday and Friday this week. We will start talking about optimization tomorrow. And tomorrow will be an overview, a motivational example that touches on different areas of optimization and demonstrates what there is to learn in the rest of the course. Today, I am ready to wrap up the presentation and begin the hands-on part in a couple of minutes. I am looking through the questions and looks like we are in a good shape. So before we do a break, I want to point out that in your interface, you have a box that reads questions, and you should feel free to type any questions that you want. Today I have help. My colleague Rio Asai is sitting next to me, and he is answering the questions that are coming in the chat window. So feel free to use this additional channel of learning. And let's take a 2-minute break. I will connect to my remote access system. You can connect to yours. If you don't have a remote access system, stay tuned, and this will be time well spent. See you in 2 minutes. Welcome back. I am ready to start the demonstration of the hands-on exercises. So if you are on one of our training servers, go to Labs, then Chapter 3, and today I will try to go through these 3 labs, and I will begin in 302. As usual, I have the code that I will be playing with, and I have the set of instructions. There is a makefile, and if I give up, I can always go to Solutions and see what we intended as the outcome of this exercise. So let me open the file. Let's look at this application. It is pretty cryptic so far. It says there are so many available threads, and then it says hello world from thread number such and such. We can compile it. And as you can see, this makefile, I believe like in the previous example too, has 2 additional targets: to run the application on the host CPU and to run the application on the Xeon Phi coprocessor. So let me try to run it on the host CPU. Well, this is not very meaningful. If you look in the instructions.txt, it explains why this is not meaningful. And it talks about the next steps. Oh, too much scrolling, I'm sorry. Instructions.txt actually guides you through it, but I remember what the instructions are, so I will just explain them here, and we will try to follow them. The purpose here is to take this application, which knows nothing about threads, and to convert this into a parallel application. We will convert it to a parallel application using OpenMP. So in OpenMP, I can query how many threads are available to me by using the support function OMP get max threads. And let me try to recompile. When I recompile, I get an error because OMP num threads is a function that is not available in the C standard library. I have to actually include the header file of the OpenMP library to do that. In Fortran, you would it would involve a use statement. You would put use omp.h. So now the application compiles. When I run it on the CPU, it tells me 24 available threads. And when I run it on a Xeon Phi coprocessor, it tells me that I have available, how many threads? 228. So what are these numbers? These numbers are the default numbers of threads corresponding to my platform. My processor is Intel Xeon E5-2630V2. It has 12 physical cores with two-way hyperthreading, so it has 24 logical processors. So by default, OpenMP will create as many threads as I have logical processors. The same on Xeon Phi. My Xeon Phi has 57 cores with 4 hardware threads on each. 57 times 4 is 228. This is what OpenMP will try to create, 228 threads on Xeon Phi. I can control this number. I can do this by setting the variable OMP num threads, and if I want not 24 threads but say 12 threads, I can set it, and now I have 12 available threads, like here. Or I can set the number of threads to 1, and my application will essentially be serialized. So let's set it to something like 4. Okay, the next line says hello world, and apparently the intention here is to print hello world from multiple threads. And this is how I will do this. I will create a parallel region, and this region has a scope, so I open the parentheses and close the parentheses. This is also applicable to Fortran, but in Fortran, instead of pragma OMP parallel, you will have I think something like dec OMP parallel, and then at the end of the parallel region, you will have dec OMP parallel end. I apologize, I'm a little rusty on the Fortran syntax for OpenMP, but it is easy to look up in the compiler manual or in the OpenMP specification. So what happened just now? I created multiple threads, and when I run, you see different threads are printing hello world. Now they all say thread -1 because I have not taught my code how to detect which thread it is running in. So here I will put another OpenMP support function called OMP get thread num. So now I actually have hello world from different threads, and you can see that the order of execution is not guaranteed. Different threads don't necessarily run the same line in this parallel region in the order corresponding to the thread number. So this is my parallel application. I've shown you how to use OpenMP support functions, how to start a parallel loop, how to query which thread is doing what, and this in principle can be enough to write many parallel applications, because well, you have multiple threads, they are running at the same time. You can get thread ID, and you can use it to identify the role of this thread in this parallel application. Before we go further, let me also demonstrate something regarding variable sharing. So I will create a variable. I will call it float a, and I will set it to 3.14. And I will print the value of f in this variable. So you can see that this variable was shared between all the threads, and different threads get the same value of this variable. Now let me create a different variable. I will initialize it to 0, and I will put the clause private b. Now let me set b here to to a times floating point value of the thread number. So b will be this. So you can see that this variable has the same value in all threads. This variable has different values in different threads. And now let me try to do something that might work or not. I will try to change the value of a. And I will set it to 0. And let's see what happens. As you can see, this is not what I intended. Let's do that. If thread ID is 0, then I will do that. So only thread number 0 will change the value of this variable. In this case, so I ran this program twice. Once I ran it, and what happened is in thread 0, variable a was set to 0. All other threads had their own value of the variable. That's because they ran before this assignment happened. In another situation, thread 0 ran first. And because it set the value of this shared variable to 0, all other threads also saw this modification. And as a consequence, all other threads had different data in different variables. So this is the demonstration of shared and private variables. We are not doing anything meaningful in our application yet, so this is just a demonstration of functionality. How to use this functionality to make the application logically correct and efficient, we will see in the next presentation. In the next lab. So this is all I wanted to pull out of this lab. So if you have any questions, feel free to type them in the question box while I go to the next lab. The next lab in 303 is actually going to do something meaningful. Now we are going to try to use threads to a good effect. We are going to perform numerical integration of a function using the midpoint rectangle method. So this is the core of my application. What it does is it initiates a loop which has a billion steps. In this loop, I choose x somewhere between the lower bound of 0 and the upper bound of 1. I do it linearly. And then this is the function that I'm integrating, 1 over the square root of x. I multiply it by delta x and accumulate everything in the value called integral. So what I'm doing is I am integrating 1 over the square root of x with respect to x from x equals 0 to x equals 1. What should I do before I begin? Let's modify this application a little bit, because in the past I've noticed that I am tempted to demonstrate some performance increases, but to illustrate it properly, I have to measure sustained performance. So this is what I'm going to do. I will create another loop, actually right here. And this loop will finish all the way down there. So I wrapped the body of this function inside the loop. Yep, and that's all I wanted to do. So now let's run this application and see what it does. So it prints out the result of numerical integration. It is close enough to the analytical result. This is what I want. The relative error is pretty small. It took me a billion iterations to do that, because my integrated function actually has a singularity at x equals 0. So this is why I have to do really a lot of steps. Of course, this is not the best way to integrate functions with singularities, but this is just an educational example. And let me also include something else here. I wrapped the body of this function inside the loop, and let me time each of these loops. And this is something that is very useful in OpenMP. I will begin by including omp.h, and then I will type t0 equals omp underscore get underscore w time. This function returns time since January 1, 1970 in seconds with microsecond precision on my platform. And I will put another one like this just before the print statement. So I've included a timer for this piece of code. And let me put a statement here, time equals, and here I will put, let's run it again. Sorry for this prep work before we begin. It will be really useful down the line. Okay, so each instance of this code on the host takes about 5 seconds. I'm going to run a system tool called System Monitor to see what's happening on my CPU. And what I see is all these logical processors are not doing anything. There is one logical processor that is running all the work. So my application is single-threaded. I have 24 cores, but I'm actually using just one core. All right. And I'm going to log this result. So I will create a log like this, which says code CPU Xeon Phi. So code, original serial code on the CPU takes 5.1 seconds to run. And now let's run it on Xeon Phi and see how long it takes. So the application is now running on Xeon Phi. It will actually take me some time to get the results. So to entertain myself with something while I wait for the results, I'm going to start mic SMC. This is the graphical version of the performance monitor for Xeon Phi. And I will go here to card number 0 and click here. This is the individual core usage on the Xeon Phi coprocessor. I have 57 cores, and I'm only using one. Even that one I'm not using very efficiently. As you can see, I have some 25% utilization. So I don't expect to get great performance out of Xeon Phi because my application is serial. And I'm not even using multiple threads per core. And cores in Xeon Phi are low clock speed cores. They are clocked at 1 gigahertz. Do I have this information here? Probably not. Okay, so the application ran, and 7.7 seconds is how long it takes to run on Xeon Phi. Okay, so let me go back to my code and see if I can improve on that using parallelism. Let's see, first of all, where I have opportunities for parallelism. This is the longest loop in my application, and I'm doing numerical integration, so I can potentially run different iterations in different threads simultaneously. So let me try to do just that. So I will parallelize this loop. Pragma OMP parallel, says brave Andre, and goes back and runs the application. So now what's going to happen? The application seems to be running. If I go to the system monitor, I should be happy. I guess all threads should be running. Ah, no, nothing happened. look, I still have one thread running, and the application takes the same exact amount of time. So why didn't it work? Did I recompile? I know this is what I wanted, but it still has to run in multiple threads. Oh, the reason that it's not running is in the previous lab I experimented with the setting for OMP num threads. So it is set to 4. Let me unset OMP num threads. Yeah, something to look out for, and run again. So now what's happening? Now I have many threads working. Yeah, good. This is what I wanted to see. But as we saw already, there is no effect on performance. That is because what I did is I created multiple threads, and every thread has the same agenda. Each thread goes through the entire iteration space, and it does the integration. Actually, the performance dropped by a factor of 2 because now 2 threads per core are doing that. I have thread contention. So instead of distributing the iterations across cores, I made all oral threads run all iterations. This is not good, and what I need to fix here is to put the keyword for. This tells OpenMP that I want to not just create threads, but also start a parallel loop. So let me rerun, recompile and rerun. So now the application is still parallel. It runs still pretty fast. It runs quite a bit faster than before. But here's the disappointing factor. The result is just incorrect. I should have gotten something close to 2, and I'm only getting 0.06. Okay, never mind. Sorry for the distraction. Okay, so let me write pragma omp parallel, pragma omp parallel 4. So in this case, the CPU time was something like 12 seconds. Xeon 5 we did not measure. In this case, the CPU time is 0.6 seconds. On Xeon 5 we did not measure because it is an incorrect result. Well, let's see what I can do about this incorrect result. The result is incorrect because I have a race condition here. Different threads with different values of I will be writing into the same shared variable integral. What can I do about this? Well, I could try to protect this with pragma omp critical. Now only one thread at a time is allowed to do that. And actually let me be a little bit more intelligent about it. Here I'm protecting a lot of operations, but I actually have to just protect the increment. So I will create a new variable called fdx, and I will set it to compute all the math. So I'm a little bit more intelligent about this. This is going to be done independently by all threads. This heavyweight square root is going to be done independently by different threads, so there is parallelism. I am serializing just this part, so let's see if that's enough or not. So I'm running this on the CPU, and I've tried this before, and essentially it takes so long that I have no patience to wait for it to finish. But the results, if I had the patience to finish, would have been correct. So pragma OMP critical is apparently just too heavyweight. I could try to use pragma OMP atomic, and with pragma OMP atomic I don't have to have a scope because it applies to just one instruction. Could try to do that. And again, if I had the patience to wait, well, let me actually demonstrate that the results are correct. I will remove a couple of zeros here. So now I'm getting correct results. But you can see, multiply this by 100, I would have to wait 77 seconds for this to finish. So let me get my zeros back and scrap this as an inefficient solution. But the results are correct. And the same here. You can experiment, reduce the number of steps, use the critical function, and convince yourself that the results are correct. So I have to do better if I want to parallelize this code. And because I am actually doing exactly parallel reduction, I can use the built-in functionality in OpenMP to do this. I can put reduction for the operation plus on variable integral. OpenMP has this built-in functionality. I'm telling OpenMP that the variable integral is shared between all threads, but what I'm doing with it is I'm only doing plus equals, plus equals, plus equals. And OpenMP is supposed to do something behind the scenes to avoid race conditions and to produce correct results quickly. So let's run. So this is looking good. The time is now 0.5, what is it, 0.58 seconds. And the result is correct. So let me type this as reduction. This is on the CPU. What about Xeon Phi? On Xeon Phi, this was very different. So look what's happening. This is the result. Should be this. So results are correct. The first iteration took a while. This is actually why I implemented multiple iterations. The first iteration has some initialization on Xeon Phi, which I cannot fully explain. But whenever you do the first iteration of a function, it usually takes a while. All subsequent iterations run quite a bit faster. At this point, I need to start suspecting, well, maybe my maybe compiler did some dead code elimination. So just to convince myself that I'm not dealing with eliminated code, let me change the upper bound. So instead of 1, I will have 1 plus t times, well, double. Yeah. So I will integrate different functions in different runs. Let me do it again on Xeon Phi. Now I know the compiler is not allowed to eliminate code, and you can see that different iterations have different results. They are correct in every iteration, but it only takes 67 milliseconds. So this is, oh, yeah, this is right. So on the host, we got less than a factor of 10 increase. On Xeon Phi, we had more than a factor of 100 increase in performance. And now Xeon Phi is much faster than the CPU. I can demonstrate that there is more to optimize on the CPU, but before I get there, I will do something else with the code. A question just came in asking, what if I don't use hyperthreads on the CPU? We will experiment with that and more in the step after this. Okay, Going back here, I included the reduction clause, which triggers some behind-the-scenes functionality which makes my code correct and efficient. I want to be able to replicate this functionality by hand because the reduction clause will not help me if I have to reduce into an array. Let me demonstrate exactly that. And this is very important because the pattern that I'm going to demonstrate is going to appear in almost all of the exercises on optimization. So if this is new to you, this is a good moment to learn. To implement reduction by hand, what I will do is I will split this pragma into two pragmas. First of all, I will get rid of all reduction clauses. And then from the first pragma, I will remove for. From the second pragma, I will remove parallel. Okay, so far I have an equivalent code. It produces the same results. It runs in the same amount of time. But this is just the first step. The second step is I will now put parentheses to indicate the scope of pragma OMP parallel. It will still compile and run the same. But now it gives me an opportunity to insert some additional code here before the loop and there after the loop. So before the loop, what I will do is I will create a new variable, integral th, and I will initialize it to 0. So this is private to each thread. And then what I will do here is instead of incrementing the shared variable, I will increment the thread private variable. Let's see what happens if I just do that. Because I get rid of the race condition. Now the code is running wonderfully fast, less than a millisecond. But what's happening is I'm actually producing a result equal to 0. That is because I never touched the variable integral in which I'm interested down the line, at the bottom line. So let me try to do that. I have partial sums, partial integrals in every thread, so now I will accumulate them all in the shared variable. Do I need a loop over threads? I don't need to loop over threads because this is still inside of the parallel region. So each thread will execute this line. It will be executed as many times as I have threads. So now let's see what happens. Now the performance is good, but the results are incorrect. See, I produced this even though I should have produced that. That is because this is a race condition, and different threads can work on this line simultaneously. I will use pragma OMP atomic to protect this line, and my claim is that this is a good solution. See, it produces results in a reasonable amount of time, and the results are correct. Now, why is the atomic construct good here, but it wasn't good before? Well, before we were trying to use the atomic construct here. Ask yourself the question, if this pragma is used here, how many times will it be applied? Well, it will be applied as many as the loop count, and this is 1 billion. Compared to using it here, how many times will it be applied? It will be applied as many times as I have threads, which in our case on the host is just 24. So I am a lot more economical in this parallel pattern with my reduction. So let me record the result. Reduction with thread private variables. This is what we call this parallel pattern. And it takes 0.62 seconds on the host. And we will know the result on Xeon Phi in a minute. So the result is on Xeon Phi is still 66 milliseconds. And the results are close enough to what they should be. So the code produces correct results. Okay, so we have been able to, before I go there, let me illustrate. If you're doing Fortran, the same procedure is available to you, but instead of doing this, you will have to declare the variable integral th before the loop, and at the beginning of the parallel region you will have to put private integral th. If I'm using private, then I have to make sure to initialize integral th inside of the parallel region. Or if I don't want to initialize it here, I can initialize it there, and then instead of private use first private. As you can see, it produces correct results. So in C and C++, you have these two ways to create thread private variables. In Fortran, it's only using this clause. All right, so let's look at performance and ask ourselves the question, is it good enough? One way I think it's meaningful to evaluate performance is by looking at the speed up, parallel versus sequential. So if we are dealing with time, we are going to take sequential time and divide by parallel time. So now let's see what happened. On the host, we had a serial time of 5.1 seconds and a parallel time of 0.62 seconds. We will compute the speed up. On Xeon Phi, we had 7.7, and then we had 0.66. So I will bring up my calculator. This is a speed up of 8.2. This is a speed up of I forgot the 0. Sorry. I can't type, can I? There we go. 117. What did we expect? I would expect that for an application like this, which essentially just does math, it doesn't really have any memory access traffic. I would expect the speed up on host to be equal to the number of cores, and the expected speed up on Xeon Phi is actually 2 times the number of cores. Why 2? That's because when you use one thread per core, you are only using every other cycle. Xeon Phi cores are dual issue. There's 4 hardware threads per core. Every thread issues instructions every other cycle. So there's cycles where threads 0 and 3 fire an instruction. The next cycle threads 2 and 0 and 2, and then threads 2 and threads 1 and 3. One cycle threads 0 and 2 fire. The other cycle threads 1 and 3 fire. If you are running everything on thread 0, then, well, it uses just every other cycle. So the expected speed up is the number of cores times 2. So in my case, I would expect 2 times 57, that is 114. Well, I got slightly more than that. That's probably because this original measurement is not accurate enough. But on Xeon Phi, I'm pretty happy. What about the host? I had 12 cores, so I expected a speed up of 12, but I only got 8.2. We will focus on this in episode number 8, but today I just want to demonstrate a quick solution. Well, one possible solution that somebody suggested is, what about I set the number of threads to 12 and try to run. With 2 threads, I get 12 threads. I get how much time? 0.42. And the speed up is now 5.1 divided by 0.42. 9.8. It doesn't, well, this is better, but still not where we want it to be. Why is this better? In some cases, well, the purpose of hyperthreads is to mask long latency operations, such as memory accesses. We don't really have any memory accesses here, so hyperthreads should not give us additional performance, but if the program is correctly executed, they should not did I compute? Then hyperthreads should not harm anything. No, yeah, computed wrong. Okay, so this seems like a good solution for this application. What I'm saying is that hyperthreads should not really harm your performance, and I'm going to demonstrate how to retain using hyperthreads, but also get good performance. Let me now set the number of threads to 24 and set one more variable. KMP affinity equals compact. This will set up binding. Well, actually, this is not. Set up binding of software threads to physical cores. We will talk more about this in session number 8. And let me try this. So this is actually not as good as I expected. But we got what we got, 0.46, something like that, seconds, 0.48. And if we set the number of threads to 12, then I have to use something else for affinity. How about scatter? Well, the proper way is compact, offset permute, so offset bring it up 1, 0. Yeah, so there is a large spread between these. Yeah, I'm not too happy with the numbers that I'm seeing. I think there's some more tuning required. And the things that I'm doing, I'm not going to explain because we actually have more episodes dedicated to just that. Looks like maybe I have some stray processes running. Yeah, looks like I do. So maybe doing this over remote desktop is not the greatest idea. But anyway, looks like this was a good strategy. Um, this strategy was not too bad. I would expect this to be the optimal strategy, but I suspect that we have some other effects that we have to eliminate before it works. Anyway, this was a demonstration of using OpenMP to do something useful, in this case numerical integration, and we used OpenMP to create threads, and we used it to control variable sharing. We used OpenMP to create a parallel loop, and we used this we used the OpenMP functionality, the atomic mutex, to protect race conditions. Really a lot of information if you have not seen this before. We also learned a very important parallel pattern called parallel reduction, where we create thread private containers for variables on which we operate using just one associative instruction. And then we use the associativity to aggregate, in other words, to reduce across all threads into the global container, and we have to protect it with atomics. This pattern will pop up many times in this course, so it is good to clearly understand what is happening here. The purpose of today's presentation is to demonstrate expressing parallelism, and we will play more with OpenMP performance in episodes 7 and 8. I would like to use the remaining few minutes to demonstrate one more functionality of OpenMP, which is tasks. And for this, I will go to lab 304. Lab 304 actually contains the same not the same application, but the same an application with the same purpose. It still calculates this integral, and the integral is calculated recursively this time. The purposes for doing that may be various. Sometimes you may want to do this to maybe work around your singularities, but in practice we saw that for numerical integration maybe this is not very useful. This is, however, very useful when you are dealing with memory access. Episode 9 will demonstrate that some applications In some applications, you can optimize memory access pattern by implementing recursive divide and conquer. So this is what I will try to do here. Let's see how this is implemented. I have this function recursive integral. It takes the range of iterations that it has to process. It returns the result, and this is what it does. There is a certain threshold. At 1,000 iterations, this function will actually go and just run a serial loop, doing exactly what we were doing in the previous case. But if we have not reached the recursion threshold, then we will go here, and here we will recursively split up. We will call one instance of the recursive integral on the first half of iterations, and then we will call the second instance of recursive integral on the second half of iterations. This program is now sequential. It runs in one thread, or serial. It runs in one thread. It takes some 5 seconds. I'm not going to focus on the value of performance here because I just want to demonstrate the principle. Let's try parallelize this application. Well, we already know that this seems to work, right? I have a parallel loop. I immediately throw pragma OMP parallel 4 reduction plus integral. And this will immediately give me parallelism. And when I run the application, it runs and runs and runs, and it never seems to finish. So let's try to understand what's happening here. It actually wasn't too bad. How many threads am I using? Yes, it wasn't too bad, but it wasn't good either. It wasn't any better than before. And to explain what's happening, let me insert a diagnostic statement here. And this diagnostic statement will tell me what I'm doing with my parallelism. Well, I should have put a line break, but anyway, you can see the principle. I have many, many instances in which I spawn multiple threads to process a tiny loop. So it's not too bad, but many, many times I have to start threads, coordinate work between them, and stop them. This is not how Intel architecture likes it. Intel architecture likes fat threads that do a lot of work between before you reassign work to them or before you stop the parallel region. So this is parallelizing too deep inside of my algorithm. I want to parallelize as far out as possible. And to do that, I will use OpenMP tasks. To use OpenMP tasks, I can write a wrapper function, but to save time, I will just put pragma OMP parallel right here in the main. And to do it correctly, I immediately have to restrict the execution to a single thread. So the initial call to this integral will be from one function. So if I run it now, oh, I should have removed this statement. Now if I run it, I will create multiple threads, but only one thread will be working. I created multiple threads, and then I restricted the execution to one thread, so I computed my integral in one thread. To make it correct, to make it parallel, I have to use the OpenMP task functionality, and I will insert pragma OMP task, and I will wrap this pragma around around the first recursive call. And is that correct? I think I will have to include the fact that So I may have an issue here. So this update will be computed. Oh, I'm sorry. Yeah, I said the first and I did the second one. Yep, now it is correct. I want to wrap this first calculation into a task. And if I do that, I will get incorrect results. Child integral is not available as outside the scope of the pragma, so I have to declare it beforehand. Now it runs quickly, but I get incorrect results. I have an issue here. I started this task. I don't know when it's going to run. But here I'm counting on having the results of this task. See, the task is supposed to set this variable. I'm counting on having it here, but I don't know if it's finished or not. So to sync with it, I have to put pragma OMP task wait. Now the application runs and it uh, still produces incorrect results. And this time I think, yeah, I specified the wrong variable here. So now it runs quickly and it produces a correct result. The performance you can measure it should be comparable to the performance with the for loop, but you can now you have this parallel pattern and you can use recursion in situations where the algorithm asks for it, the serial algorithm asks for it, or maybe where the uh, memory optimization tasks ask for it. So this is it for today's hands-on presentation. As mentioned, tomorrow, tune in again, same time. We will start talking about optimization, and I will demonstrate the optimization of an n-body calculation, and we will touch on scalar tuning, tuning of factorization, tuning of multi-threading, memory access traffic, and communication to some degree. If you have any questions, then after I finish the webinar, you can type them in the question box and we will answer with text. Otherwise, thank you for your attention and see you all tomorrow. Bye.